Alright, hello everyone. So these problems are dealing with specific heat problems, which basically is a transfer of energy from one object to another. And so I'm going to go through two example problems in case you're stuck at home. These may be helpful to you, maybe not. But the first problem that I'm going to give you guys is it says, what quantity of heat is required to raise the temperature of 450 grams of water from 15 degrees Celsius to 85 degrees Celsius? The specific heat capacity of water is 4.18 joules per gram degrees Celsius. Okay, so the first thing is what equation will I be using? And that is given to you right here. This was talked about in the notes in one of the lessons. All right, so that's the equation I'm going to do. So basically it's the change in energy, which is the same thing as Q. Q is heat, equals MCAT, mass times the specific heat of whatever the object is times the change in temperature. How much energy or heat is required to raise this water from 15 degrees Celsius to 85 degrees Celsius. And basically you just are going to be plugging numbers in. So as always, I recommend writing down your knowns and your unknowns. And so the mass of this guy is 450 grams. So I have 450 grams. The T final is going to be, it looks like 85 degrees Celsius. And the T initial is 15 degrees Celsius. And then the specific heat, C, is 4.18 joules per gram degrees Celsius. Okay, so this is just basically a plug and chug type problem. So what I'm going to have is I'm going to have 450, which is my mass, times C, which is 4.18, times T final, which is 85, minus T initial, which is 15, and these are degrees Celsius. And what does that equal? And whatever that equals, that is my Q. And if you bust out your calculator and you do your order of operations correctly, where you take the subtraction problem first, you should get a Q of 1.3 times 10 to the 5th joules. All right, 1.3 times 10 to the 5th joules would be the amount of energy needed to raise this water temperature from 15 degrees Celsius to 85 degrees Celsius. And as you can imagine, if there was more water, it would take more energy. So if I had, like, say, 6,000 grams of water, it would take a lot more energy than, say, 450 grams and so forth. Okay? So that one I think is pretty self-explanatory. The second one, I apologize for the font size, but I wanted to have some space to work, is a little bit trickier. It involves a lot of thinking here. It says a 12.9 gram sample of an unknown metal at 26.5 degrees Celsius is placed in a styrofoam cup containing 50 grams of water at 88.6 degrees Celsius. The water cools down and the metal warms up until thermal equilibrium is achieved. So basically that means that both objects are going to be at this temperature in the end, which is 87.1 degrees Celsius. Assuming all the heat is lost by the water and is gained by the metal, and the cup is perfectly insulated, so there's no outside factors going in here that some of the heat is lost to the atmosphere or any of that kind of junk. Determine the specific heat capacity of the unknown metal. And I will tell you that the specific heat capacity of water is this number right here. Okay, so again, we're going to be using this equation, but the big key here is that you understand that the amount of energy in the cup is not going to change. The total amount of energy is constant. And so whatever heat the water provides to the metal and is lost is gained by the metal. There's no additional energies here. So basically, this equation right here is going to be set equal to itself. And this was taught or discussed, I should say, in the lesson 2 video. Because basically what you're going to have is you're going to have this, I'm going to put like question mark metal the Q of the question mark metal has to equal the Q of the water, which is H2O. So you can basically set these two equations equal to one another. But before I get too far ahead of myself, I want to first write down my knowns and unknowns. I'm going to try to do this where I don't take up all the space on this thing. So my question mark metal, what do I know about it? Well, I know that it has a mass of 12.9 grams. And it has a initial temperature of 26.5 degrees Celsius. Do I know a final temperature? And the answer is absolutely. It says that the water and the metal will warm up until thermal equilibrium is reached, which is 87.1 degrees Celsius. So that involves a little bit of like intuition on your part that you're able to figure that out, that thermal equilibrium means that both objects will be at this temperature of 87.1 degrees Celsius. Do I know the specific heat of this object? And the answer is no. So I'm going to put that as a question mark. I don't know that. That's what I want to find out, right? That is the goal of this question. And do I know how much energy was gained by this object? And the answer to that, as of right now, is no. That is the question. So I have two unknowns on this side. Okay, this unknown metal, these are my knowns and unknowns. Then over here I have water. What do I know about my water? Well, I know that the water has a mass of 50 grams. It has a initial temperature of 88.6 degrees Celsius. I know that it has a final temperature of 87.1 degrees Celsius. How do I know that? Again, it's because thermal equilibrium was reached at 87.1 degrees Celsius. Do I know a specific heat of water? The answer is yes. I tell you the specific heat capacity of water is 4.18 joules per gram degrees Celsius. Do I know the Q? And the answer is no. And this is the whole key to this problem. If you can find this Q, then whatever that Q is, it equals that Q. And that really is what unlocks finding out C, because then you only have one unknown in this mysterious metal. And I'm not able to figure out how to put a calculator up here at the moment, so I promise you I'm doing this work on a calculator, and when I crunch my numbers using this formula for water, so if I had taken 50 times the specific heat of 4.18 times the change in the temperature, which is T final, minus T initial, so 87.1 minus 88.6, and those are degrees Celsius. I apologize, my handwriting is so bad on this. Hopefully it'll get better as I do it more. What does that equal? Now notice this is going to come out to be a negative, and so this is a great opportunity to talk about negative Q. If you get a negative Q, what does that mean? It means that object lost heat. It was giving away heat, and there's nothing wrong with that. You can certainly have a negative Q, and this water is going to lose some heat. Where is it going? It's going to this metal that was put in this styrofoam cup. So this equals, if you crunch this number in your calculator, and correct if I am wrong, but I got negative 313.5 joules. So that Q is what's going to unlock the specific heat for this metal, because basically what I can do is I know that this Q is actually positive, right, because it gained heat. So the equation for this, and I apologize, this is getting be real messy here, it is 313.15, because I'm just taking that Q and plugging it in to the equation up above, equals a mass of 12.9 times C, which I don't know, as I'm trying to find out, T final, which is 87.1, minus 26.5. Barely got that in. And basically, if you do the algebra here, you get a specific heat of, I'm getting 0.40, 2 sig figs, for a specific heat of this metal. And again, this is a much harder problem than the first one that I did with you guys, but it really puts a lot of good principles into play here, where you have to know that because the system is isolated, that there's no additional heat gained or lost by the styrofoam cup, you can then set these Q's equal to one another. And that frankly is the hardest part of the whole problem, is if you can figure that out, that the Q metal of this mysterious metal equals the Q of the water, then you're sitting pretty. If you have any more questions, feel free to talk to me in class, and we'll see you guys in the next video.